All right, let's have a look. 13H applications. Let's take this first example. Paris has a painting that is valued at $100,000 and is expected to increase in value by 10% per annum. And that's probably the key part to recognize and understand. So it increases, unlike linear. So linear, usually you say like every hour increases by $1, or you might say every year increases by $100, right? So that means every single year, you know, it's a constant amount. This one, on the other hand, it's 10% per annum. So yes, every year increases by 10%. 10% is constant, but 10% of a value is not always constant. Okay, and that's where you start to see the differences between a linear graph and an exponential graph. So here, write an exponential rule to model the growth where A is the final value. So how much will it be worth, this painting that Paris is invested in? How much would it be worth after a certain amount of time in years? So T is the time in years. So after 3 years, if T was 3, after 5, how much is the painting worth now? So they invested $100,000, and if it grows 10% every year, how much is it? Now, before we get into the modeling of it, which is this whole first bit to help you model it, let's recap on our knowledge on percentages. How do you calculate the value of the painting after 1 year? So if I asked you right now, you knew Paris invested $100,000, so 100K. And we want to know that if it increases 10% per year, so every year increases by an extra 10%, after 1 year, so if T equals 1 year, how much is it worth? And how do you calculate that now? How do we do that? So this is a basic year 8, year 9 mathematics here. How do I find the value of the painting if you spent $100,000 on it, and by the end of this year, it's going to increase by 10%? It's like your shares, those who keep talking about Bitcoin and all that. So you invest $100,000 of it, increases by 10% this year. How much will you have now? How'd you work that out? Let's go with Artie. How would you work out if you invested $100,000 into this painting, and you know by the end of this year, it's going to increase by 10%, how much will it be by the end of this year? So after 1 year. You might need some time to think. 110. Now, how'd you do it? Not sure. You did get 110. I want steps here. How do you do it? So he said $110,000. He said it will be worth 110. How did he do it? Okay, say that again. So you said $100,000. And you said times by? Why 1.1? This is the key. This is where I'm actually wanting you to understand where it comes from, because that's where exponentials comes in. But a lot of students don't see that bit. Where does 1.1 come from? Do you know, Anthony?
It's like 10% is the big one, and like the one where it's 3 was.
Very good. So normally, back in year 8 and year 9, when they first do this, how you would do it first is I'd say, well, what's 10%? After 1 year, by the end of this year, how much is 10%? So the kids, I have to teach them. I have to say, well, what's 10% of 100,000? So they'll go, well, 10% of 100K. They have to go, well, that's 1 or 10 out of 100, which is 10%. Of means times, and you do 100,000 like that, right? Now, just out of curiosity, my year 8s have to learn what they call unitary method, so they can do that in their head. But what's 10% of 100,000? Lucky. 10,000. We just simply divide it by 10 if we know that it's 1/10. So divided by 10, so that's 10,000. So you got $10,000, but then what do you do? So the year 8s go, okay, so I know 10% by the end of this year, I'm going to earn an extra $10,000. So what they have to do afterwards is they have to go, well, you start off with 100K, $100,000, plus the extra 10%, which now is that extra 10,000. What you can see is why is it 1.1 is because 100,000 was equal to 100% of itself. And you added on an extra 10%, which actually is the same thing as saying you're finding 110% of the value. But 110% of the value is actually just the same thing as saying 110 over 100 or 1.1. So the concept here is that every time you say, what's 100K or an extra 10% of the amount, you're actually timesing by 110%. That's what you're actually doing. Because instead of doing 10% of that amount and then add on to the original, there's 2 steps there. We can actually simplify that step. Instead of that addition, we can say, well, that's the same thing as just finding 110% of 100,000. Okay, so all you had to do in this step here was when you increase a value by 10%, it is the same as multiplying by 1.1. Because when you're multiplying 1.1, so $100,000, your starting value is $100,000. It was just quicker to actually times it by 110%. Because that together actually already means your original amount plus, which your original amount was $100,000. So yeah, $100,000 plus extra 10%. So once we understand that now, that was the key step here. Multiplying by 1.1. Okay, because that 10% was actually a 1.1, you're an extra 1/10 extra of what you started off with. So let's look at the mathematics and then hopefully you can see where exponentials start to apply. So we know the technique is the original amount, so I'm going to write here original, times by 110%, which is 110 over 100 or 1.1. So if I start off with the calculations, here we go. Year 0, you put in $100,000, still worth $100,000, right? But you have to wait till a year later. So 365 days later, then they'll increase. If the bank says, yep, you still got this money here, they'll increase the value. Or in this case, the painting, if you kept it for 365 days, it increases by 1.1 or times by 1.1, yeah? So here you would then say the next one is it's $100,000 times by 1.1. Now, Artie said before 100,000 times 1.1, we know that is $110,000. So he's correct. What's interesting is the next step, and hopefully you see my working out and then you can see where indices comes in. Next step is, well, now it's $110,000. If you were to work out for the value for the second year, if I said you held it for another year, you would actually then say, well, isn't it just $110,000, which is what it currently is, added on another 10%. So if you do another added 10%, you do times 1.1. True? Now let's do it on a calculator. What's 110,000 times 1.1? What does that give you? Oh, mine's going to take a while. Can someone calculate that quickly? What's 110,000 times 1.1? I'm going to have to use my CAS on this phone. If someone's got it, call it out. 121,000? No objections? Everyone trusts? Yep. All right, done. 121,000 then. So $121,000. Now, that isn't what I'm interested in. I'm not interested in this bit. I'm interested here. See, how does this become exponential? See, if you look at it, $110,000, if I highlight it again, wasn't this the same value as that? But that value is actually from this calculation. So why can't I take this calculation and substitute it here? Because if I do that, what's the benefit of doing that? Is that it actually then gives you $100,000 is what you started off with. That's the benefit. You don't need any more values. You don't need to know 121. You don't need to know 110. You just need to know how much you started off with. So this is your original amount. You had to times this by 1.1 to get your 110. That's your 110,000 there. But then you had to times another 1.1 to get to 121,000. But can you see there's a repetition here? 1.1 times 1.1. What can we write that as? Instead of writing the actual answer, what's a simplified version? What's 1.1 times 1.1? Using indices. It's like saying 3 times 3. 4 times 4. We would say squared. Because you're timesing itself twice. So this was actually easier to say in the second year, isn't it just $100,000 times 1.1 squared? So this starts to see a pattern. you start to see a pattern that first year, 1.1 was actually not there. It's 1.1 times 0, or to the power of 0, which is 1. Here, after the first year, so year 1, it's 1.1 to the power of 1. Year 2, it actually ends up being 1.1 to the power of 2. Then you start to see this pattern that it works that if you do the same thing for the third year, you would have said it's 121,000, but 121,000 was the same thing as writing this line. So you can replace that line again. So you can replace that line. So if I take this line, that's 121,000. So if I replace that, instead of saying times by 1.1, I can rewrite it as $100,000 times 1.1, and then we did times 1.1 again. So this is your 121,000. You see that? That's my 121,000 times by the extra 1.1. Whoops, sorry, I forgot this square here. But each time we do it, there's a repetition again. See that? 1.1 squared times 1.1. We know indices, same bases, add the powers. So that it becomes, your formula is $100,000 times 1.1 cubed. So that's for the third year. So now if I ask you, once you see that pattern, I can ask you, well, what about the 99th year? You can still do that. You see that? That's the benefit of being able to generalize. Whereas if I didn't simplify it before and I kept it, your problem is you don't know what the 98th year is. See, this one, unless I knew it was 121,000, I needed to replace this with 121,000, but I don't need that anymore. I just need the original. That's the benefit. The benefit of being able to rewrite that in a different way with indices is you only need the original amount and there's a repetition of indices. That's why it happens. Okay? All right, team. So let's have a model. So let's answer the first part now. So I've guided you through the first bit so you can see how the modeling happens and why it happens and why repeated multiplication indices or index laws leads to, in this case, exponential graph, right? Because we're doing that 10% every year. Now, the first question was, can you model that? A is the final amount, so how much the painting will be worth. What's the pattern? So T is the number of years. We can see that when it's 3 years, it's power 3. If I asked you 99, it would have been 100,000 times 1.1 to the power of 99. So if I asked you now, what if it's T years? How would you model it? What's the formula? A equals, who wants to have a go? Milana? Beautiful. That's it. That's the modeling. And that's how, if you look at the, like later when we flip over the page, the formula for your general, whether it's growth or decay, that's what this exercise is about. You don't really need to memorize that because it makes sense of what you're doing. Otherwise, you end up memorizing whether you subtract or whether it's a negative. It's none of that. You don't have to remember the compound interest formula back in year 9. That you have to remember this is A, and that's principal times 1 plus R over 100 to the power of N. You don't need that because that literally is what we just did. We just did the exponential proof to it. But if you didn't get it, then there's a formula for you to memorize. And that's how it works. Okay, but I like it that if you understand it because that means you can model. If you can model, you can then problem solve. If you don't, you just memorize up until a certain point. If you do enough questions, then you'll know how to approach most questions. But if you don't do enough, and you don't get it, then obviously applications becomes really tricky to figure out. All right, so now we've got a model, and then they say part B, what is it? How much will his painting be worth after 4 years? So this is now a straightforward point. We can say if T equals 4, how much is his painting worth? And then based on our model, we can say it's $100,000 is how much he began, times 1.1. That 0.1 is that extra 10% to the power of 4 because that's number of 4 years. Type this in your calculator. So here we go. I'm going to plug it into my calculator. Though it's not loading. No, it's not loading. All right, here we go. I'll do it on my nice nifty phone. 1.1 to the power of, where's to the power of button? To the power of 4 times $100,000, which is what you began with. It's $146,410. So $146,410 $410. Okay, if you got that answer, it means you typed in the calculator correctly. I'm sure you shouldn't be able to do it wrong. Since I can do it on my phone, then you should be able to do it on your CAS calculator. Question C, though. What is C saying? So how long will it take for his paintings to be worth $500,000? How do we do C? So let's say Paris only wants to sell his painting after he knows it's worth $500,000. That's when he's happy. He's going to hold it on, but he doesn't know how long he's going to hold it on for. So how long will he have to hold it on so that it's $500,000? So again, you can try to picture this by reading the graph. You can sketch it. Think about it. That's your dilation. That's your base. There is no vertical translation, no horizontal translation. So you can expect the graph to look something like this. So the question is, how long? How long before? So when will T be so that you reach 500K? So there's a certain point on the graph. When will it reach 500K? That's what you're asking. So you know the Y value has to be 500K, 500,000. Let's work it out. You solve. Very good. So yes, very good. So if you have a CAS calculator, this was your formula. A is equal to $100,000 times 1.1 to the power of T. We know that the final amount we want is $500,000. So it needs to equal to 100,000 times 1.1 to the power of T. Here you can solve it by hand. If they want exact values, this is an application. It did say round to the nearest year, so it means you can use a CAS. So at this point, if the question was an exam 1, then we want you to actually show us the algebra. If it isn't an exam 1, you're allowed to use a CAS in your notes, then here you're meant to use your CAS to solve. Okay, do it quickly, otherwise you'll spend time doing it by hand. Yeah, so here, meant to use a CAS. Now my CAS is not really working at the moment, so I can't show you. But if we were to do it by hand, we'd divide both sides by 100,000. 100,000, this divides itself. 500,000 divided by 100,000 gives you now 5 is equal to 1.1 to the power of T. So out of curiosity, so far, if this was an exam 1 and not a CAS calculator 1, how do I find T? I want T in exact value. How would you do this? Very good. So, well, not multiply, you log both sides by 1.1. So you'll be doing log 1.1 on the right or left, and then you do log 1.1 on the right. Log 1.1 of 1.1 cancels out. So T is equal to log 1.1 of 5. If you have a scientific calculator, then you have to change your base rule. You could do log base 10 and then rearrange them. But in this case, because you guys have a CAS, it is possible to type on your CAS what log of 1.1 of 5 is. Okay, now I can do that on this phone. So let's do, can I do it? No, I can't. I have to do change of bases. All right, so it'd be log 10 of 1.1 divided by log 10 of 5. Yes. Did you guys get 0.059219? Is that what you guys got? Looks a bit odd. Oh, I realize it's the other way. Whoops. No, you shouldn't get that. You should get 5 over 1.1. That looked weird. 16.88. 16.8863. Is this what you guys got? Good. So it says to the nearest year. What would the nearest year be? 17. And logically, that's because right at this point, that's 16.88 right here. So that's exactly that year, but that's still within a year. We want the next closest year. So it can't be 16. 16 would be before 500K. So to be more than 500K, I'd have to go to 17. Okay, so you could say nearest one would then be 17 years. to guarantee that his painting will be worth $500,000 or more. Okay, so even if this was 16.1, like 011, you'd still round it to 17 because you want that 500K. Okay, so the nearest year, if you say 16, it's technically not 500,000. So you have to be careful with those application questions. You want it to the nearest year to make 500K. So if minimum was 16.01, then you have to round it to the next year, which is 17. Okay? In this case, it was a bit easier. It's 886. All right. Any questions for that? That's pretty much what you're doing for exponentials, but it's hopefully tying it a bit better than your previous years where you're just memorizing a rule and applying, but hopefully you're seeing how index laws get repeated and then how you're using the graph to visualize what you're answering because you're analyzing the graph. Okay? All right, team, now let's flip over to the back. You're going to try those two questions here, but here's your two formulas. Here's the two formulas you would have seen. On the back, they call it a growth graph because this is 1 plus the percentage. This was the 10% that we were doing before, right? The 10% that you're adding extra. So this is your compound interest formula, but just written differently. This is your final amount. This is your initial amount. This is the percentage you're adding on. Right? And then T is the number of years. Notice in decay, it's minus. Now, why is it called a decay? Well, 1.1 we saw before is going to go this direction. What happens when you minus? So 1 minus, let's say 10%. So if you reduce, let's say his painting was losing value over time, or stock market's losing value over time, it's 10%. Why is it called a decay if I minus it? Someone explain to me. Why is it that 1 minus 10% becomes a decay? Very good. Now let's think about the logic. 1 minus, let's say 10% is 90%, right? But 90% is 0.9. If I asked you to sketch 0.9 to the power of t, remember we said if a, the base value is between 0 and 1, if it's a fraction, it's actually a reflection along the y-axis. The graph actually ends up being this way. Okay, because it means that for every year that is increasing, it's reducing. So that's what's representing here, that every year that you go this direction, the value is dropping by 10%. So it makes sense in this graph. So it means that if you have negative time, which doesn't exist in an application, but if you did have negative time, it actually starts to increase. Okay, so if you put in, I don't know, -2, for example, that value starts to increase rather than decrease. That's the difference between it. Okay, so that's why we call it a decay. So one is a growth graph, and then the other one's a decay graph. And all it is just what is the base value? Is it a decimal or is it more than 1? If it's more than 1, obviously it's going to grow. And if it's less than 1, between 0 and 1, it's going to decrease. So these next two examples, I want you to have a go with them. But that's essentially a similar modeling to your exercise book. They're essentially just giving you a model. You have to then figure out what type of modeling, how do I do it? Is it a growth? Is it a decay? Some questions will be a bit tricky, like this one is a nice one. I like this one because of the wording. So it might be worth looking at example 32 of your textbook. It's just the wording that you model, but how do they cancel out that initial values? That's a nice problem solving one. So question 32, have a look at that in your spare time there. But what I want is you only work on 13H if you're up to date. If you're not, go back. I want your algebra done. So A, B, and D is your algebra for exponentials. And then you got 13E. Was it E? Was it F? F and G, the log rules. So those are your algebra component. And your graph's only 13C for exponential. And I think it was 13G. Yeah, I think it was 13G for logs. Okay, so E and F might have been the algebra. So you want to do algebra first, then your graphing, then applications. Okay, so tomorrow's one is algebra. Tomorrow's one I'll be testing your algebra and sketching. I'll give you a bunch of logs and exponential equations, and then I might ask you to sketch it, but I won't be asking you to do applications like this. Okay, I'll be asking you just to solve, sketch, show me algebra. Okay, I'll stop the video there, and you can have a go with these. I'll write the solutions right afterwards.